This is the polymer chemistry course with the English teaching class, and of course, as you well know, this is the open courseware course. So you know, the staff's recording this class, but don't be afraid about your OCW. This is the polymer chemistry course, and welcome to this polymer chemistry. And as I have shown you in this leaflet, this course is for the 16-week class, and I have elaborated a little bit of what we will be teaching, what you will be learn about during this semester. And first week is just an introduction about the polymers, and I will make slides for you, so that this slide or PowerPoint file is uploaded in my website, so that you can download it before you come to the class. So I hope that you can read and have some questions about what you will be asking to me, and I will of course ask you some of the other questions as well. And there are some questions in these slides as well. Right? So before you come to the class, hope that you can read the materials that I will give you, and also about the chapters. Okay? The textbook is written in the middle of the leaflet. This is the Introduction to Polymers, which is the 3rd edition. And the author of this book is Robert Young and Peter Lowell. Okay? This was published in 2011. So you can find in the bookstore, or this is just an introduction of the polymers. So you can read other textbooks related with the polymer chemistry as well. Okay, but according to what I have listed for the weekly assignments, for example, the 2nd week is about the molecular weight. Okay? So if you can find the other book related with the molecular weight, I think it's about the same. Okay? But each week I will give you some of the assignments to you, so that you will be presenting your assignments after 1 week. Okay? So you will have several assignments and homeworks for this semester. If you look through what I have written, I'm located in the 9th floor, which is the same floor as this room. And my office hour is written in there, Wednesday and Thursday, 14 to 15, or any time if you can find me. Okay? I have the position at the administration, so if you cannot find me, you can email to me so that we can make the reservation for you. Okay? Or I can answer and returning to your email. Okay? And Wednesday and Friday at 9 till 10:15 in this room is the time and location about this class, and I have already talked to you about the textbook. Okay? Lectures are basically as the lecture is recording. This is mostly what I will talk to you. Right? But we will have 2 exams. We have a midterm exam in the about 8th week, which is about April 20th or something, and you have a final exam as the other course. But as you can take a look at in the 3rd page, page number 3, 15th and 16th week, you will be given topics, so that about the polymers. And I will, make a group of people, okay, 4 or 5 people, for a topic, so that you will present about the 15 minutes in English for the final 2 weeks. Okay, This way, I think we will be better understand what you have been, done learn, and what you will be doing in the polymers. Okay? With that, I think if you have any questions about the course, then I will take it. If not, I will give you some of the examples of the introduction of the polymers. Any questions about the course? Okay. Okay, let's begin about the introduction then. Eh? Well, have you, perhaps this is the long and old the drama or cinema called the Graduate. Eh? The Graduate. We have Dustin Hoffman. Dustin Hoffman's character was written here, and there is a big, I don't know what it is, but perhaps you know what this is. This is the lady's leg with a stocking, and he says, I just wanted to say one word to you, just one word. And she was saying that this is the plastic. And this film was recorded in the 50s, and they said it's a plastic. So do you know what the plastic means? Or have you heard about the plastics? Well, stocking is stocking the plastic? Yes? No? Yes? Oh, yes. Okay. Well, some of you have answered that the plastic is a stocking is a plastic. Eh? Okay. Well, I said, well, there might be some difference between the stocking and plastics. Stocking is made of fiber, actually. Okay, but not plastics. Plastics are different from fibers, isn't it? Well, actually, this is the plastic, right? It's not fiber. It's not stocking. And they said, well, the plastics, they don't care about at the time, about 60 years ago, they could not figure out the plastics and polymers and fibers at the time, perhaps. Well, you are living in the world of plastics, of course. You have a lot of plastics. You have coffee cups and bottles, the polyester bottles, your tea bottles, plastic bags with the everything, almost everything is made of plastics. So you all know what the plastic means, but perhaps you heard a lot of times about the plastics. Well, I just wanted to ask you one question. Can you read?
Where can we find the use of polymer in our ordinary life?
Perhaps you understand, right? Well, have you heard about the polymer? Polymer, what is the polymer?
Big, very big molecular weight and
Okay, that's correct. That's correct. He said the polymer is defined as the material with a very high molecular weight. Okay, the molecular weight is one of the characteristics of defining or distinguishing the polymer with other materials. Other materials, such as low molecular weight compound, is what we call is a monomer. Okay, polymer is made of monomer reacting consecutively to form a long molecular weight components. Okay? Anyway, the question is, where can you find the use of polymers in our daily life? Just like a stocking, just like a plastics, what else? Can you find other polymer examples from your friend or of yourself? Can you name me? You know what it is? Okay.
Nylon.
A nylon, okay. Nylon is a polymer. So can you find the nylon from your daily life? Socks, yes. Nylon socks, nylon stocking. Okay? Stocking at the time, the plastic is made of nylon at the time. Nylon. Can you figure out the chemical structure of nylon? Oh, that's difficult. Right? Difficult at this time, but yes, that's a good example. If you all know, you don't need to come to the polymer chemistry course. So this is why you come to here to learn about the chemical structure of nylon. Nylon is the same. In other words, do you have other nylons? Do you have many types of nylons or just one type of nylons? Many types. What kind? Nylon 66, nylon 610, nylon 6, something like that. So you have many types of, there are some numbers after nylon, right? Perhaps you'll learn about it when you have a organic chemistry course or in your the chemistry course as well. Anyway, what else? Nylon. Can you name? Rubbers. That's correct. Rubbers. Rubbers are also the type of polymers. Okay? Where can you find the real rubber?
You can find it in tire or eraser.
That's correct. Yeah. Well, he said that the rubber is a type of a polymer, and could be found as an example of a tire, pneumatic tire in your automobile. Okay? It's made of rubber and it's a polymer. Okay? Rubber. What else?
Plastic bag.
Plastic bag. That's correct. Plastic bag. Just like this bag. This is made of vinyl. What you call is a vinyl. Vinyl, and it's made of a polymer. Okay? Can you figure out what kind of polymer is this? Polyesters or polypropylene or something like that, right? So you can find other films. What is the bottle is made of? What is this bottle? Can you just erase? Okay, what is this plastic or is this rubber? Plastic. So you said that's not a rubber. What is the difference between the plastic and rubber? Flexibility. Is rubber flexible than plastic? Okay, right. I think you all know about many of the other information about the polymers. Well, that's very correct. Rubber or a tire is flexible, isn't it? Okay, tire is flexible, or eraser is flexible. Whereas this plastic, the bottle, that's made of polypropylene or polyester. Right? The bottle is less flexible. Right? It's a little rigid. What we call is the rigid, and it's the difference between the plastic bag and the rubber as a pneumatic tire. What else? What else? Well, this is the word. And I have exemplified with the fiber stocking. Fiber is one of the example of the polymers. Fiber, you are wearing the fibers. You are wearing the clothing made of the fibers. So we have a fiber department formally, but they changed the name to organic nano, 유기나노 공학과. Okay, organic nano engineering department was formerly a fiber department or textile department. They're studying about the fibers, right? Only the fibers at the time. But they're expanding their area to the other polymers as well. But fiber is mainly their expertise. Right? Fibers, what kind of fibers do you know? What type of polymer can be used to make the fibers? I'm wearing the shirts, which is made of cellulose. Okay, cellulose. 면, 우리는 말로 면이라고 하는 거. Cellulose. Cellulose is also a type of polymer. Perhaps you couldn't figure out what's the structure of the polymer, but cellulose can be widely used to make your the fiber and your inner shirts, okay, and pants and as well. What else? I think you are wearing your acrylic fiber. Is made of polyacrylonitrile. You are wearing your polyester fibers, sweaters, which is made of polyester. Same chemical structure with the bottle plastics. Okay, you can make a fiber out of polyester, or you can make a plastic out of polyester. Okay? Those are the two examples of fibers. And you have many of the other types of fibers, just like nylon 6, nylon 66, nylon 610. And of course, you can also make the very distinguishable fibers, such as the Kevlar fiber. Have you heard about the Kevlar? Okay, Kevlar fiber can be used to protect yourself, armed garments, or the bulletproof clothing, okay, so that you can protect yourself. And the bullet cannot penetrate through this Kevlar fiber, so they can protect you as human beings or protect your buildings, walls, and tanks, and others. So fibers can be used in many of the applications. Plastics. I told you that polyester, the same polymer, can be used to make the fiber as well as plastics. There are many types of polymers can be used to make the plastics. Rubbers. Rubbers are usually made of the butadiene type of polymer, okay, or isoprene. Have you seen the rubber tree? Rubber tree, perhaps in the picture or in the movies, but rubber resin is coming from the rubber tree, particularly from the Southeast Asian countries where you have rubber trees, big rubber trees that contains a lot of double bonds in the monomer and polymers, and later on you can cross-link them to make a very resistant to the adhesion as well as chemicals and thermal stabilities. So we'll tell you how you can make the rubbers. And elastomers. Elastomers and rubbers are basically the same, but elastomers can be used to make your polyurethane and 쫄바지. Okay? You have elastic fiber as well, so that you can make your shape. Okay? Okay? And coatings, perhaps coatings. You have paints. Okay? You can see a lot of paintings in the wall, on the wall, and those coatings are also a type of the polymers. Okay? Coatings can be used to make also the coatings can be used to make your film. On top of your film, you can find a lot of coating materials. For example, can I take a look at this bottle? Okay. You have a film. Perhaps you have a film, and this film or plastic was coated with some characters. Okay? But I believe this film or the plastic was treated with something so they can coat on top of this film or fiber or the plastic. Coating will alter or change the characteristics of the surface so that before the coating, the plastic was not able to be coated because of the hydrophobicity. But if you change the characteristics of the surface, then it could be coated with the inks. Okay? Anyway, I think we can talk about it later, but coatings are also a type of the polymers. What else? Oh, it says protein. Okay? Protein is a biopolymer. Okay? Protein, well, your body is made of protein, and this protein is made of very monomeric units, which is called amino acid. Okay? Amino acid contains one amine group and one carboxylic acid group with a CH and some of the substituent group. So this is the basic component of amino acid, will polymerize to become a polypeptide, and it's what we call the protein. So our body is a polymer, basically, okay? Because it's made of protein. And all the animals are made of protein, so that we can call them as a protein, polymer as well. So we have a live and the biopolymer. We have, of course, the dead polymers, which is made of, which will make the various types of very usable materials, which will be used in our daily lives. Cellulose, I told you about the cellulose, which is very important to make our fiber, as well as wood component. This is the wood component. So wood is basically made of the cellulose. And of course, the other components like a lignin, but wood is also a type of polymer. Adhesives, finally. Adhesives, well, you can think of your 3M Post-it tape. This Post-it tape can adhere with something, and it was coated with adhesives on the backside of your the paper or tape, and this polymer, this is made of polymer as well. Usually this is made of methyl acrylate, which is a polymer. You can see that the polyoctamethyl acrylate is a typical chemical structure of the 3M Post-it note, and it's very expensive, I believe, and they make a lot of money. Anyway, those adhesives and the various types of other, many of the other things are examples of the polymers. And you can find many of the other polymers examples if you click in this file, so that it will go directly to websites. For example, for example, you can see many of the other examples if you click each of them, so that you can see many of the other examples other than what I have presented. Okay. Okay. Well, this is the slide where you can find very famous guy. Famous guy, Mr. Kim in North Korea. But he was, looks like he's very happy taking some kind of fibers. Okay, this fiber is exactly the same as this fiber. And this fiber is called binalon in North Korea. And the reason I'm presenting this is that they are very well presented in this polyvinyl alcohol fiber, okay, polyvinylone fiber. Actually, this vinalone was first made in 1936 in Japan, Kyoto University. The Professor Sakurada and yes, Professor Sakurada and Dr. Lee Seung-gi. At the time, he was a student of Professor Sakurada, and those two made polyvinyl alcohol polymer at the time for the first time in the world. 1936, about 80 years ago. Okay? And the reason I'm presenting is that Dr. Lee was assistant professor at Kyoto University at the time, but after the Second World War II, he came back to Korea and became a professor at, of course, the Chemical Engineering Department of Seoul National University until the Korean War. And during the Korean War, he was, his father took him to North Korea, and I was told that Dr. Lee became the very top level or director or president of the North Korean Academy of Science. Okay? Well, the reason I am presenting is that at that time, during the 50s and 60s, his father supported Dr. Lee very much about this chemistry of polymer and their invention about the polyvinyl alcohol, so that there should be a big plant nearby the Hamhung and Wonsan, because there is a fertilizer plants at the time, and those chemical factories were converted to polyvinylone manufacturing sites in North Korea. And I was told that everybody, including him, including the leader, is wearing the polyvinylone fibers. Okay, vinylone fibers. But this vinylone was not made from crude oil, not from the petrochemicals, but from the coals. The coal chemistry was very different from the petrochemical chemistry, so that during those 50s and 60s, South Korean level of the polymer industry, well, chemical industry, was behind the North Korea at the time. Of course, if you can look through the GNP of the North Korea and South Korea at the time, we're a little behind. Right? But after the 60s, evolution of petrochemical industry, we were much developed. And right now, we are not using this polyvinyl alcohol for the fibers. Okay? But instead, this is the example of polyvinyl alcohol with a fiber. But this same polyvinyl alcohol is made in Korea right now by Dongyang, the petrochemical company, and they make the very high molecular the polyvinyl alcohol in order to, this is the example of the chemical structure, to make the films. The films, polyvinyl alcohol films, can be used to make the polarizing film. If you can take a look at this LCD monitor, every LCD monitor have this polarizing film, which is made of polyvinyl alcohol with the same chemical structure. Right? So, with this polyvinyl alcohol, you can make a fiber, just like in the case of North Korean, or you can make the film and can use to make the very high valued products, such as this. If you can have the digital camera or digital watch, or everything that is made of digital, you should have a polarizing film. Okay? Those polarizing film is made of polyvinyl alcohol, and I just wanted to show you what is the polarizers. Okay? Just a second. Okay, this is just one film using this polarizer, right, made of polyvinyl alcohol. It's a little bit darker than the just transparent film, okay? But you have a protecting film. You have a protecting layer. But anyway, I think you can find the little bit of a dark cases. And I have a second film. When I overlap this film, you can clearly see there is no difference. Okay, but if I will make it overlap in this way, looks like perpendicular way, there are clearly a different colors. So it's a little much darker. Okay? The reason why we have this little darker region is that, okay, this is transparent again, it becomes dark, okay? Is that this film was oriented, okay, oriented or stretched, and the iodine, iodine solution was embedded in this films and make it a little bit darker. So this way, this film was a stretch in one direction, okay, in one direction. This is what you call the polarizing. If you look back to the organic chemistry course, there is a section about the polarizer. Okay? The light will go to the one direction, okay, with the polarizer. So that in the UV, ultraviolet instrument, the polarizing, the theory is very important. Okay, what we call the Beer-Lambert law. Anyway, if I have a two oriented film, and if I will overlap in the same direction, there is no difference. But if I will make it perpendicular to the orientation, then it will become very dark. This is the way of making the liquid crystal display. Okay? Of course, there are some liquid crystals, but polarizing film is very important to make this digital instruments. So every digital instruments that I have told you must contain this polarizer, okay? One way or another. Okay? You can make a very thin film, or you can make a little darker film. You can just cut it, or large films, or whatever. It will be used anyway. So in Korea, although we are a little behind in terms of the fiber manufacturing from the polyvinyl alcohol, of course, we were much advanced in using this polyvinyl alcohol in this way. Okay? And this is the second example of the use of the polyvinyl alcohol in this industry. And you can, using this polarizer, you can make a goggle, okay? Ski goggle, okay? And that way you can make a high valued products, of course. Using the polyvinyl alcohol, this is the third example, you can make a coating material. Okay? Coating materials such as, I'm sorry about the example from the US, but anyway, this is the glue, white glue. You can make the glue because this polymer has a hydroxyl group. This is CH2, and CH and OH. So you have a hydroxyl group in polyethylene. So polyethylene, if you do not have hydroxyl and just the hydrogen, it's a CH2 and CH2, so it's a polyethylene. Right? Polyethylene does not have any hydroxyl group, so that polyethylene itself is hydrophobic. If you put the water on top of the hydrophobic material, the water drop will, move very smoothly. But if you have a hydroxyl group, the water will adhere, absorb to this polyvinyl alcohol. So polyvinyl alcohol is water soluble, in fact. It's water soluble at a little warm temperature, around 85 degrees C, but at room temperature, it's not. So temperature sensitive, the solubility is coming from the hydrophilicity of this polymer, with the hydrophobic in nature in the backbone. Anyway, this polyvinyl alcohol can be used to make this glue, or you can make it. Well, there's a fiber here, and you can usually polyvinyl alcohol is widely used. What you call in Korean word is 풀 매긴다는 거 있죠. It's kind of glue. Okay, it's a kind of glue for the fiber or fabrics. Okay, so it's a little different between what you can do. Anyway, in the fiber industry or fabric industry, polyvinyl alcohol is very widely used to make your fiber in a fixed conditions. So it's widely used in adhesives for the papers and paperboard in the packaging. Every paper that you're using, the white paper, they also contain some polyvinyl alcohols as well, okay? Because it's a kind of glue. You can make you can use this polyvinyl alcohol in the fiber reinforcement in the concrete. Okay. Anyway, in the architectural application, in the concrete application, you put the fiber, but the fiber itself and concrete will not adhere together. So when you treat your fiber with the polyvinyl alcohol, and the concrete will be very well mixed, or the interface between the concrete and the fiber is very well formed because of the hydrophilic in nature of this polyvinyl alcohol. Okay, so those are the examples of the polyvinyl alcohol, and could be used in many of the other applications. Let me ask you the stupid question. Well, you have a very nice hair. Okay? Your hair is basically black, but I have a little white hair. But hair, the thickness of the hair is about 70 micrometer. 70 micrometer. This hair is not like just like a fiber. Okay, it's a fiber basically, but this fiber is not like the fiber that you have seen in this case. It's an artificial fiber. Okay, you can make a very smooth fibers, but in this fiber, the hair is a natural fiber. This natural fiber has a little bit of a rough surface, just like a plant. If you look at very carefully with your microscope, okay? Is the hair polymer or not? Polymer. Why it's a polymer? Well, yes, it said protein, but basically it's made of protein, but I heard that this is made of keratin. Okay? But keratin is a type of protein, just like your nail, hair, okay, is made of keratin. Well, if you look at the cow, I don't know whether this is the correct word or not, but cow nail is pretty big, very big, and it's made of a keratin basically, and keratin is a type of proteins. This protein is widely used to make a lightweight concrete blocks. Lightweight concrete blocks. when you mix the solution of this keratin solution from the cow and mix it with the concrete, you make a bubbles, okay? You make a bubbles. When your concrete is fixed later on, because of the bubbles, you make a lot of pores. You make a lot of foams, right? And the density of your concrete is much smaller than the concrete without any pores. This way you can make a lightweight concrete. Okay? So lightweight concrete is widely used in making your apartment. So polymer is used even in the architectural applications as well. Okay? Lightweight construction. And this project, the lightweight keratin solution, extracting the project was my first project to my friend when I came here in 1988. Okay? So he found a company, and he's right now becoming a businessman with this solution. So for the last more than 25 years, it was very successful, and he has the factories in China as well. Anyway, you can this keratin is main component of the hair, and it's a little different from the natural fibers. I mean the artificial fibers. Okay. Well, if you know about the type of the other polymers, I think it would be nice, but because this is the first time, I think I have to tell you. This is the type of the questions that I will raise during the class if you have read the material. Okay? I will tell you about the homopolymers and copolymers, tacticity, conformation, and configurations. Well, can anybody tell me about the difference between homopolymer and copolymer? What is homopolymer? Just one type of monomer? Okay. And what about copolymer? Several different? Okay. Okay. Well, looks like although it's not exact, I think what I can interpret it means that this homopolymer is made of just one monomer. Okay. If you use two monomers, and this two monomer will become polymer, then we will not call this as a homopolymer, we will call this as a copolymer. So homopolymer and copolymer is coming from how many monomers do you have? How many types of monomer that you have in your polymeric units? Okay? So if you have only one monomeric units, such as polyvinyl alcohol, we call that as a homopolymer. Okay, but if you have two types of monomeric units, we call that as a copolymer. Can anybody tell me about the example of copolymer? Okay, we have an example of acrylonitrile. Acrylonitrile was used to make a fiber, just like acrylic fibers. Okay? Fiber with rubber. Okay? If you put the fiber and rubber, monomeric components in one polymeric units, it becomes flexible fiber, or rubber with a little stronger material property. Okay? So using this concept, I think you can make various types of copolymers. For example, polyacrylonitrile polyacrylonitrile has a chemical structure. If you go back to alcohol, instead of this hydroxyl, you have a CN group. This is polyacrylonitrile, replacing the hydroxyl with the nitrile. Okay, CN group is what's sometimes called cyano group or nitrile group. So acrylonitrile is a main component of the acrylic fiber. But this acrylonitrile, because of the dipole-dipole moments of the triple bonds, is very strong. Because of the repeating units, the CN group is repeating every other carbons, right? So the CN group is getting together, so it forms hexagonal rings, and those rings have a dipole-dipole moments, CN, and it becomes a very strong material. It becomes a crystalline material, in fact. And polyacrylonitrile, 100% polyacrylonitrile, is very difficult to dissolve in organic solvent, and it's very difficult to make it the fiber form. So 100% polyacrylonitrile is very expensive, but the reason why you have a very cheap acrylonitrile sweater is that they added the small amount of the second monomer, okay, sometimes methyl methacrylate or acrylates with the acrylonitrile, so that they cut those CN dipole moments. That way, I think you can make the soluble acrylic fibers. Okay. Anyway, that's the type of the examples of the copolymeric systems, and we'll take a look at other examples as well. Have you heard about the conformation and configuration? Of course, yes. Can you differentiate between these two? For example, have you heard about the isomer? Cis isomer and trans isomer. Okay? Cis isomer and trans isomers are example of conformation or configuration? Configuration, that's correct, configuration. Cis isomer and trans isomer are totally different chemical. Okay? You cannot make a cis isomer to become trans isomer. Cis isomer is a cis isomer, and trans isomer is a trans isomer. The configuration is spatially is a different structural the chemicals. So configuration you cannot change. Okay? What about the conformation? Have you heard about the helical structure? Helical structure of the amino acid. If you have a double-strand, double helical structure, what do you call this? Yes, DNA is made of a double helical structures. This double helical structure or a helical structure is not permanent structures. It could be defolded. It could become zigzag structure. It could become random structure with the same chemical structure. Okay? The conformation, okay, that I showed you is that alpha structure or alpha helical structure or beta structure or gamma structure. Alpha, beta, and gamma structure are the examples of the conformation. This conformation is a spatial okay, arrangements of the chemicals in the space. So this is spatial, not special, but spatial, S-P-A-T-I-A-L, spatial arrangements of the chemicals can be changed. So conformation depended upon the environment, okay, such as the solvents, the temperature, or exterior environment, and could be changed. However, the configuration is just a fixed arrangements of the chemicals, so that you cannot change these configurations. What about the tacticity? Have you heard about the tacticity? Perhaps not. Okay, perhaps not. Okay. Well, we will tell you about a little bit more about this tacticity. But have you heard about the polypropylene? Okay, polypropylene has a chemical structure with methyl group in this polyethylene units. Okay. If you have a methyl group in every 2 carbons, methyl group, okay, zigzag structure with a methyl group. This methyl group containing this carbon has just 1 hydrogen, and this is what we call the alpha hydrogen. This is the beta hydrogen. You have 2 beta hydrogens. This alpha hydrogen is very susceptible to the attack from the UV light, so that when the polypropylene film is exposed to the air or light from the sun, this polypropylene will become degraded. Okay? So polypropylene vinyl film, okay, wrapping your greenhouse will become a little stiff after 1 year, 2 years, and 3 years. So after 5 years, the greenhouse film is totally different from the fresh film. The reason is that there is a degradation of this polypropylenes. Anyway, this polypropylene can be used to make the films. If you go to the mart, okay, supermarket, you will see a lot of examples of your, packaging films. This packaging film is quite strong sometimes. You can put those the watermelon, very big watermelon, with the films even. Wow, that's very it has not been happening in the 70s and 80s. We were always using the strands or vinyl strands to carry those watermelons. But nowadays, because of the advancement in technology, even the polypropylene film can be used to carry those very strong the watermelons or heavy watermelons. Well, the difference between the very thin film of the polypropylene and little flexible one is coming from how this methyl unit is spatially rearranged. Okay? In other words, I think I have a slide. So I think we can talk about it, tacticity. We have 3 types of tacticity as well, of course. Atactic, isotactic, and syntactic, depending upon how this methyl group is rearranged. If the methyl group is in the same position, we call it as isotactic. If the methyl group is in every other way, in opposite directions, we call this as a syntactic. Or if there is any random fashion, in sometimes downward, sometimes upward, but there is no rule or order, then we call it as atactic. So tacticity will determine the density of your final polymer, particularly the polypropylene. So the reason why we have those tacticity is coming from the use of use of the catalyst. Okay, we will talk about it later about this tacticity. So this is the main examples of the chapter number 1 about the scope of the polymer chemistry. Okay, so we'll go in a little bit more detail of each. Okay, I think we have already talked about the monomer. We have already talked about the polymer. We have already talked about the molecular weights. So the first question that I have raised was that the definition of the polymers. Polymer is made of the monomer during the polymerization reactions. Okay? So monomer is very important to make your polymer, right? Monomer. Oh, well, there is a word called the dimer, trimer, oligomer, and polymer. Okay? Do you know what this di, tri, oligo means? Mono is a Greek word, and it's a combination of the mono. This is the counting the number. Okay, mono is just one. Di or bi, just like a bicycle. Tri, tetra, hepta, hexa. Excuse me. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, right? This is just counting the 1 from 10. And so this is number. More means molecules. More means molecules. So monomer says just one molecule. Dimer is 2 molecules gathering together. Trimer is 3 monomer coming, attaching together is what we call the trimer. Oligomer, oligosaccharide, oligodang. Oligo means several monomer, several. Several is not a definite word. It doesn't count 4 or 5 or whatever. It's just a several. Several is a non-definitive word. So oligo means, well, we have several monomers. We don't know of which number that we have. Okay? It could be 7, it could be 10, it could be 5, it could be 3, it could be 4. Okay? So oligo, it becomes oligomer, and it becomes polymer finally. Polymer, poly. Poly means many. Okay? Poly means many. So you have many molecules. So molecular weight is many or high. Okay? Is the meaning of this polymer. Well, you have an example of ethylene. Ethylene looks something like this. You have a double bonds between this carbon and carbon. Okay, the double bond has sp2 hybridization carbon, okay? whereas the CNH carbon or CH3 has sp3 hybridization carbons. So the double bond is opening to make a radical or to make ions, and it becomes polyethylene. Now we have repeating units, so double bonds is open to become a radical, and this radical or electrons will meet each other, connecting to the other second monomer units. That's why we call this as a slash over here. We have a bracket, and N means this CH2 unit is repeating n times. N times. So this is the monomer, and this is the monomeric unit. Monomeric unit. It's not monomer, but monomeric unit, repeating n times. And later on, we call this as repeating units. Okay, repeating units. N is called the degree of polymerization. Degree of polymerization. So if you know the molecular weight of these repeating units, and if you know the N, then you will know total molecular weight of your polymer. polymer molecular weight is not the same as monomeric molecular weight because it's repeating n times. N typically is over 200. N typically is over 200 to make your fiber, to make your polymer, to make your plastic film, to make your whatever. So if you know this repeating unit molecular weight, which is about 28 right now, right? It's 12, 2, so it's about 14. It's about 14, so the molecular weight of a repeating unit is about 28. If you multiply 28 by 200, it becomes 56,000. So it's a kind of the number over about 50,000 or 100,000, sometimes 200,000 in that level is a basic molecular weight of the polymer. Okay, we have other the example. We have a hydroxyl group. We have a carboxylic acid. Hydroxyl and carboxylic acid will react each other because of the SN2 reaction, okay, nucleophilic substitution reaction. So this hydroxyl will attack this carbonyl. So you remove this hydroxyl from here and hydrogen from here. And it becomes ester. It becomes ester. If you just have only one monomer, then there is no reaction. But if you have two monomers or higher number, then hydroxyl, because of the two unshared electrons, this hydroxyl will become nucleophile, so that it attacks the carbonyl. So you remove this water out of this one monomeric units. So it becomes ester. Okay? We call this as ester or ester units. You still have hydroxyl and carboxylic acid. Okay? We call this as a dimer. This dimer, of course, because of the two functional groups left at the end of your chain, it will be capable to conduct further on to become the trimer, tetramer or quadrimer or whatever. It becomes oligomer and polymers, of course. Now, you have a repeating, you have this unit is repeating n times in this case. So repeating unit is a little different from this case. But anyway, the molecular weight of your final component is the molecular, if you know the molecular weight of your repeating units, if you know the N, okay? N is like a dimer or a trimer and so on, then you will know the molecular weight of your final components, right? Okay. So we know that the monomer, dimer, trimer, and so on becomes a polymer, okay? So poly means many, and well, many molecules are getting together to become one molecule. Many molecules become just one molecule. But there are some other words called the macromolecules. Macromolecules. Macro means big. Big. It sounds like a big molecule. Well, big molecule is understandable because we have a bigger molecule, much bigger molecule than monomer molecules. Okay? So macromolecules and polymer are the same. Okay? Polymer was widely used in Europe or whereas the macromolecules are sometimes used in U.S. and so on. But anyway, I think there is some mixture of the terminology, and there is no distinction between polymer and macromolecules. It's right now, there is no confusion. It's the same word, so you understand that sometimes they use a macromolecules or sometimes they use a polymer. Okay? And we know that repeating units, we know the degree of polymerization. So if you know the molecular weight of the repeating units times the n, which is the degree of polymerization, you will know the final molecular weight of your components. Okay, so we have general equation is that if you have a monomer M, representative as M, monomer N, and N, small n, is a number of your molecules, number of your moles of your monomer. It conducts a polymerization and becomes like this molecule. So we have many molecules in this case, but we have just one molecule, right? So this is the example of the polymerization reactions. So chain length becomes bigger from the smaller chain length. Molecular weight becomes bigger compared with the monomeric units. In reality, what you do is that you have a beaker or flask. You put the monomer and catalyst. If you heat it up, it becomes polymer after some time. Okay? And sometimes they put the pressure. Sometimes they put the catalyst in different cases. Sometimes they put the extractor. If you boil them, there are some byproducts coming out, such as water. If you remove the water, then it changes your equilibrium so that you have a further reaction to become polymerization reactions. Okay? So you will have an experimental energy class in the 10th floor, and you will be able to make the polymer by your own. Now, you have an arrow here. This arrow is coming from left to right. Left to right. Sometimes if you have arrow, okay, arrow in the the x direction or the left-hand direction and the right-hand direction, okay, it means that it will be in sometimes the equilibrium. Okay? Monomer and polymer has the same condition, so that there is no further reaction. If you have if you find the arrow coming from left to right, then means that your monomer will become polymer. If you find the arrow from the opposite direction, right to left, polymer will become monomer. That's what we call degradation reaction. So polymerization and degradation and equilibrium, if you have both of the arrow, so you have three types of the thermodynamic stages. Thermodynamically, you will need to move your direction to become more favorable to polymerization reaction, in this case, by making the arrow from left to right. Okay? Left to right. Now, how can you move this arrow from left to right? I told you that there is one trick to remove the byproduct so that you can break the equilibrium and make the arrow from left to right. Okay, so we will learn about how we can move those equilibrium and to make your final favorable product later on in this class. Well, I will just make the this slide here with another example. Another example of the polymerization is that you will make the another glue with the polyvinyl acetate. This polyvinyl acetate is widely used in making the wallpaper glue. wallpaper glue, 그 벽지 바를 때 그 뒤에 쓰는 그 glue 있거든요. 풀. There is a white wallpaper glue, and which is made of polyvinyl acetate. The chemical structure is about the same. It looks like this, and if I will write in here in this way, it looks like. So this is polyvinyl acetate, and you see that you can just only change this substituent group from nitrile, hydroxyl, nitrile, methyl, or acetate. By changing those substituent group, you have a different type of polymers and different type of the property of the polymers as well. If you have a hydroxyl group, it's water soluble. If you have a methyl group, it's not water soluble, but make it very hydrophobic. It's water soluble as well because of the hydrogen bonding capability with the water. It's not water soluble, but it becomes very strong material because of the dipole-dipole interaction between the cyano groups. So material property depended upon the chemical structures. Anyway, you can make a polymer. You can make a polymer out of this vinyl acetate, and it's very important in industrial applications. Now, there is an example of the exercise where they ask that N, in this case, is a 500. So repeating unit or degree of polymerization is about 500. Molecular weight is about 42,000 because the molecular weight of this repeating unit is about 84 because the C is 12, 12, 16, 12, 16, and it's about 15. So if you add up, I think it's about 84. So if the molecular weight, if the degree of polymerization is about 500, then the final molecular weight is about 42K. 42,000. And I think they are talking about the average degree of polymerizations. So you will know about the molecular weight in here. And one of the last slide that I have to show you is that material property depended upon the molecular weight. I told you that the dP should be at least 200 to become a polymer in making the reasonable property. If the molecular weight is low, for example, 10,000 or 20,000, then material is not imparting the right property. Okay? If the molecular weight is over 10,000, 20,000, so it says about 42,000, then you have a right property of the materials. Right properties such as elasticity. Okay, rubber should have elastic property. Plastic has a little rigid property. Fiber should be a very crystalline property or semi-crystalline property. Okay, in order to have those property, you should have a right or sufficient molecular weight. If the molecular weight is not enough, your fiber, if I will just grab, then fiber will be broken. Okay, the plastic film cannot be formed. Plastic bottle cannot be existing without any sufficient molecular weight. So material property, whatever it is, looks something like this depending upon the molecular weight. If your molecular weight is high enough, then you can maintain your property, mechanical property or thermal property or chemical property. Whereas if the molecular weight is low, then property is something very below the standard or average. So you should have enough degree of polymerization for your final property of materials. Okay. With that, I think I can stop here for this chapter. And please, we should upload the file to the website of my homepage. And please read, and we can speed up next time. Okay? Okay, if not, I will see you on Friday morning. Okay, thank you.